Excuse me. Hello, welcome to Biochemistry Simplified. We're here for yet another exciting lectures on example problems with acids, bases, and buffers. It's been a long journey on acid, bases, titrations, and buffers. It's been very exciting, learning a lot. Now, in this lecture, we're going to be looking at some example problems, calculations with acids, bases, okay, titrations, of course, acid and base leads to titrations and buffers. So, welcome you once again to this channel, Biochemistry Simplified with Dr. Elik. Thank you for joining at this time. Okay, so I'll just go ahead and let me do this in blue. So we're looking at example problems. Example problems with titrations, and that includes acid and bases and buffers. Great. So, excuse me. In looking at this lecture, actually, we are not just solving problems. There's a need for you to understand the chemistry and allow the chemistry to guide the mathematics and not the other way around. So it's not all about mathematics and solvings, but understanding the chemistry behind every question here is key. You can always stop to check what reactions is actually taking place. That way, you'll be able to always be guided. If you do not understand the chemistry, you are going to be limited in the number of problems that you will be able to deal with. But this is biochemistry, and there tends to be a lot of things going on around the questions that you'll be seeing. They are not a very difficult problems or questions, but it's just a question of understanding the chemistry behind it. So we'll just jump right in to take example one. Example one, we do that in red. So our very first example, example one. So we have glycine, an amino acid, glycine and amino acid. So let me just quickly give you the structure of glycine here. Okay, so you have C, H, H, and you have C, double bond O, OH. So you have this um, amino moiety right here. Then you have the OH group. All right. So you can actually demarcate it like this and indicate this part as your arrow group. Okay. So that is it. Glycine, an amino acid, is often used to prepare buffer. It's often used to prepare buffer. So glycine is often used to prepare buffer solutions in biochemistry. So in this case of glycine, we'll say let's concern ourselves. Take another color to do that. We'll say let's concern ourselves with the reaction that is going to take place. So let's go ahead and write the equation and write the reaction that is going to take place. Okay, so if we write out that reaction, it gives us this. So we say arrow representing glycine, the arrow group attached to your amino group NH3. Okay, so as it is like this is the protonated form. This is the protonated form of the amino acid. This is the protonated form of the amino acid glycine. Okay, so if we look at this reaction carefully, we'll have this as arrow NH3 plus. If this undergoes dissociation reaction, you have your H plus your arrow NH2. Your arrow NH2. Alright, so right here is the acid, which is your glycine, and right here is what? The conjugate base. Okay, so that's the reaction, and in this reaction we have a pKa equal to 9.6, and this pKa is actually the pKa for the amino group. The pKa for the amino group. Okay, so in this reaction we are considering a buffer solution in this reaction right here. So right here we have a little bit of a buffer system here, a little bit of a buffer system. So this way we have actually brought out the chemistry around the question, what the parameters given glycine. So let's look at the question proper on the next page. So question A of continuation of that example is, what is the buffering? What is the buffer region? What is the buffer region of the amino acid? What is the buffer region of the amino group for glycine? Okay, and the question 2, let me just give the question 2 ahead. Question 2, which is question B, it says in a 0.15 molar glycine solution at pH equal to 9.2, at pH equal to 9.2, what percent of glycine, what percent of glycine is in its protonated, what percent of glycine is in its protonated form. Okay, so that those are the two questions before us. So we take it one after the other after understanding carefully the chemistry of glycine. So we say answer or solution to that question you have. We want to recall the buffer region. The first question say what is the buffer region? So we want to recall that recall that the buffer region is pKa plus or minus 1, and that actually shows a range. So from our question, a pKa of 9.6 was given. So pKa equals 9.6. Therefore, it implies that the buffer region is 9.6 plus minus 1, and that gives you a range of 8.6 to 10.6 as the buffer region. And that answers question 1. So as such, if we are going to run an experiment that will require a pH in that range, glycine buffer is a good buffer. So with this buffer range, any experiment that you intend to run that is within this pH range, glycine buffer is a good buffer because it falls within the range. Okay, so we now go to, this is for question number A. So we now begin question number B here. So the question reads, in a 0.15 glycine solution at pH 9.2, what percent of glycine is in its protonated form? First, you want to know the form of the reaction that is what? Protonated. So we write that the protonated form of the reaction is, so writing out that reaction equation again, arrow, which is your representing your amino acid glycine, you have forward backward reaction. H plus is given off to form your conjugate base NH2. Okay, so again, this is the acid and this is the conjugate base. This form as it is, this conjugate base right here, is the unprotonated form because it's the one accepting the proton. It's not giving out the proton. The proton has been given up and it's formed the conjugate base. So this form here is the unprotonated form. Why this form here, all right, why this form here that is the acid that is giving off the proton is referred to as the protonated form. So this is the protonated form of the amino acid glycine. This is the protonated form for this reaction. For the reaction, which is the acid. The acid is the protonated form, while the conjugate base is the unprotonated form. Thus, the protonated form is the species that have the proton H plus to donate. So worthy of note, MB, okay, we do that in blue for emphasis. So you MB, you say thus the protonated form, the protonated form is the species that have the H plus, that have the hydrogen ion, which is the proton, to donate. That's very key. So it's very important you know what is donating the proton to be able to clearly identify the protonated form, which of course the question directed what percentage of glycine is in its protonated form. So we'll continue to solve this question. We say from the question they want to know the percentage of glycine that will be in its protonated form. So percentage in its own is a whole. Percentage implies a whole, is a part of a whole. Percentage is a part of a whole. And the whole is 100%. So percentage is a part of a whole number or integer, and the whole in this case of percentage implies 100%. So to solve that problem, let's go ahead and use the Henderson-Hesselbalch equation, which is perfect for this case as follows. So you can put that down using the Henderson-Hesselbalch equation. You have the following. Using the Henderson-Hesselbalch equation, you have the following. So the Henderson-Hesselbalch equation says pH is equals to pKa plus log, in this case the conjugate base is RNH2 concentration over the acid, which is your RNH3 plus. So applying that Henderson-Hesselbalch equation, we are given a pH equal to 9.2. We are also given a pKa, which is equal to 9.6. So we just substitute that into the equation, and what we have is we also want to represent this here as just concentration of the base over concentration of the acid. So right here, this will represent B for base, and this will represent A for acid. So if we slot all of that in, what we have is 9.2 is equal to 9.6 plus log concentration B over concentration A. So this ratio here, this concentration B over A, we are solving for it as a ratio, this right here, because we are looking for the percentage. So you're going to solve for this, as, sorry, okay, so you're going to solve for this as a ratio, okay, and that ratio, as a ratio, which is the concentration of the base over the concentration of the acid. All right, so what we have, if we do that, we have 0 minus 0.4, that's taking the numbers to one side. You have minus 0.4 is equal to, okay, log concentration B over A. Okay, so taking the antilog and exponential to base 10, you have taking the antilog and exponentiate to base 10, exponentiate to base 10, you have the following. Exponentiate to base 10, you have the following. You have the following, okay? And what you have is 10 to minus 0.4 is equals to 10 to log exponential concentration over A. All right, so what that gives you is 0.398 is equal to arrow NH2 over arrow NH3 plus. Of course, remember we in our previous solving we have said that let RNH2, which is your conjugate base, be the base represented by B, and the acid represented by A. So what we have done here is to simply replace it back. So replacing that back, you have your RNH2 over your RNH3. So this is the ratio as it is right here. The ratio of the base, which is the unprotonated, to the acid, which is protonated. And that gives you this number right here. So this implies the ratio of the base, which is unprotonated, to the acid, which is protonated. And that is equal to 0.398. So we have gotten for the unprotonated. So converting this value to percentage right here, you have 0.398 times 100 simply converts it to percentage to give you 39.8%. And this 39.8% is what? Unprotonated. Okay? So, and this is because the RNH2, which is the conjugate base, is part of the whole. So we have 39.8% that is part of the whole as unprotonated. So what you have noticed is this is because the concentration RNH2, which is the conjugate base, which is the conjugate base, is part of the whole, is part of the whole, and the whole in this case is 100%. However, the question is asking for the protonated form of the glycine. If you go back to your question, it says what percent of glycine is in its protonated form. So the question is asking for the protonated form and not the unprotonated. Thus, to get the protonated form, thus to get the protonated form, you do the following. To get the protonated form, to get the protonated form, you do the following. You do the following. That is the whole, which is 100%, minus the 39.8% of the unprotonated form, and that gives you 60.2% of the that shows that 60.2% of the acid is what protonated. So 60.2% is actually the percent that is protonated, which the question is asking. So this right here is the answer to that problem. So note that in this case, the ratio itself was used. The numerator or the denominator was not solved for as per concentration.